Okay, so what about we just start?
Yeah.
Okay, so today's guest is Murat Kantarcioglu from UT Dallas and Harvard University, and he's going to give a presentation on secure, private, and fair AI. And this one.
Thank you. So, what's this area? I don't know how many people are watching online. The one thing I wanted to mention is that I cannot hear you if you're online, and if you have a question, please type it. Because of the setting here, you need to type the questions if you want us to hear these questions. So I'm going to talk about my work in the intersection of security, privacy, and AI. And it's here. Okay. Of course, as I mentioned, my work is intersection of AI, security, privacy, and and of course, I don't need to explain to this crowd and this team that big data change everything. And of course, part of this big data change is this cloud, AI, ML, and of course, because of this huge amount of data, everything's kind of reinvented. From security point of view, at least my research point of view, I always very worried about cyber attacks and protecting data while we are doing all this important thing with the data. At the same time, the privacy is an important issue that I worry because of not only the regulations, but also we need a way to protect this, simple and effective way to protect this data while doing all the useful things, and also really need to comply with the regulations. And I think it's just starting like GDPR in Europe is an important part in data privacy world and the regulations related to it. And of course, not only that, we need to worry about the cloud, whether you outsource data to cloud to build your machine learning models. Nowadays, it's very hard to build a model at home, or at least in even universities now. So you may need to outsource to cloud and do cloud computing. And also learned AI and ML models could be vulnerable to attack. There's this adversarial machine learning area that's being heavily studied, which also I worked on and told some of things. And of course, when you're deploying ML models in practice, it has huge privacy and security implications. So over the years, I work on different aspects of these challenges on the intersection of the security, privacy, and fairness. And I'm going to talk about some of the work we have done, highlighting some of the challenges we try to address. One issue we started was, I don't, yeah, I couldn't get rid of this stuff. I don't know if I can use this stuff for this else. Since I shared it at the same time. Okay. So basically, one issue we looked into earlier on is how we protect this data against while training AI models, machine learning models.
Yes,
Sorry. Mine is muted because they are hearing from here.
Oh, yeah, hearing it from the other one.
Yeah, so I joined from my laptop. That's the reason you see this bottom part, unfortunately, because I'm sharing my screen. So technical difficulties, let's put it that way. One of the early works, as I mentioned, like to how to really secure this data while doing processing and so on was using encryption. And of course, one idea was like how to encrypt data during storage and processing and still build the models. One thing we looked at, this was published in a cybersecurity conference called CCS, was using some hardware called Intel SGX. These are also known as trusted execution environments. And today it's under the topic called confidential computing. And NVIDIA announced a new chipset called, I think, H100, where they have such an execution environment for GPUs. What are these trusted execution environments? This is a hardware-supported security model. And what this Intel architecture or similar trusted execution environments such as NVIDIA brings you is that you have, and the CPU has a part of the chip where you could have execute an encrypted component, okay, or encrypted data inside this memory location. The data is automatically encrypted by the CPU. So this enclave will not be able to observed by the operating system or the hypervisor. So any data that is processed, assuming the hardware is trusted, will be protecting against any other malware running on the system or operating system or the cloud provider. And this is not, and the reason I chose this that because I think this very practical today. And the reason is that Microsoft has something called confidential computing cloud that allows these chips to be used, and they have all these tools. So today you can deploy this solution, unlike some other crypto solutions. And similarly, Google have a similar solution based on AMD chips. So this is very applicable today compared to some other work we have done where we use crypto and so on. And of course, so what this hardware can be used for is that you can use this hardware to protect the secrets and integrity of the data and doing machine learning models. And of course, you can do all of this leveraging this chip. And our goal was to have a generic framework where data scientists can write their machine learning models by leveraging this encrypted data processing capabilities by the CPU. And because of the way the CPUs work, this trusted execution environments work, you have to worry about data leakage. And what I mean by data leakage is that if you write a simple code such as this, where you try to use the average income for individuals in a given pandas vector, let's say, if you write such a code, even if the data is encrypted, even if the hardware is secure, this code will reveal memory access patterns, because whenever this condition is satisfied, this part of the computing memory will be accessed, and therefore it would leak the memory access pattern on the data. So you can look at even if everything is encrypted, even if the memory is encrypted, you can look at this memory access patterns to infer some sensitive information about the encrypted data. So therefore, building secure applications, generic applications for data scientists using these confidential computing chips is far from straightforward. So what's the solution? One big leakage is this memory thing. So in our case, we do something called oblivious computation, and that's the main challenge. What it means is that this code in our system will be written something like this. Here, this statement here will return a 0-1 vector, and you are getting the dot product of that vector divided by sum. So the important part of this code is whatever the underlying data, the code execution will access the same memory locations. So therefore, the memory leakage would be limited. Hence, it won't disclose these important informations. Of course, there are lots of other system challenges which I won't talk about. And one thing is that in order to even use this efficiently, you have to have a compiler.
One question.
Sure.
When you do that access, the thing in quotes person need.
Yeah. It will return you a vector of size, whatever the vector of original thing, and it will if that tuple satisfies that condition, it will have a 1, otherwise it will have a 0.
Okay,
so it will go over all the tuples and create the one vector.
I understand, but somebody will be able to track when that happens.
No, because remember, memory is encrypted totally by the CPU. So you can only see memory access patterns, but not the memory contents. But here, even if the data is encrypted, by seeing the memory access patterns, you would be figuring out how many people are bigger than 50, assuming you know the condition is that. So this is a very important part of leveraging confidential computing resources securely. Of course, there are other things, but this is one of the important parts. So you need to hide these memory access patterns.
So this happens at the programming language level, or introduced any programming language.
So our main introduction is that we devise the entire kind of Python subset where you don't have if clauses, and instead we have oblivious versions of something like this, so you can do almost all machine learning stuff.
Like what you have at the bottom, that's kind of how you do it in pandas, right?
You can do it in pandas too, but yeah, you would need to do oblivious way. So we have oblivious. So in other words, oblivious that means that it doesn't change based on the underlying data, the memory access pattern. So we have basic constructs that are all oblivious, and when you combine them, it's oblivious. So whatever the data distribution, assume no one is above 50 or everyone is above 50, it will always do the same memory access pattern.
Okay, so saying that, so that's what pandas do. That's how you write it in pandas, right? But you don't know whether once it compiled into machine level.
No, we guarantee that because some of the pandas, like joins, for example, we rewrote them so that they are all oblivious. We developed this framework, and of course, you write it something like in pandas, and then we transpose it into like intermediate thing in our language using our building blocks, and there are lots of optimizations which is not so much important for this discussion. And then you can run this, and there are other challenges. This is like some kind of intermediate output of our compiler. If you have such an input, it will write it as this intermediate steps and do the thing. And there are other features that are needed. For example, intermediate results may have sensitive outputs. So we analyze the code to make sure that the data scientist who is using this encrypted data platform doesn't leak accidental information. One leakage, for example, is that if you use this, for example, here, there is this summation, right? Imagine you use this summation to create a vector, certain vector size. Then you will leak this sensitive sum value. So we looked into the code to make sure that it doesn't leak anything. And also we do optimization. And the reason is that the SGX chips have lots of buffer management issues, so you have to really manage it, then optimize it. So what does this gets you? By using this hardware, compared to like regular solutions, you can easily process things on using encrypted data, such as linear regression or PageRank. These are just examples we chose. We tried other things in seconds, and this is again for older data sets and older times, so the times are slightly faster. And compared to encrypted solutions, one comparison, something like Oblivion, which doesn't use hardware, it just uses pure encryption. Our difference is that we leverage this hardware, so therefore we have this additional trust component. But compared to encrypted solutions, even in a simple metrics, when we do encrypted data processing, we could get much faster performance. So this is an example where we try to protect the data for machine learning while we process it using a secure hardware and encryption. Of course, as I mentioned, I'm giving a little bit overview of all these areas that I worked over the years. Of course, the other model is that maybe we don't even need to share data to protect data, even if it's encrypted. Maybe you don't want to ship the data to a cloud provider, or one important thing in the GDPR type of things, shipping outside the countries. So one area that we also looked at was federated learning. This was work in AAAI 2 years back. And in that work, we looked into, I'm not know whether everyone is familiar with federated learning, but just to recap, the way federated learning works is that the server or the initiator of the federated learning would initialize a model. Let's say here you are trying to learn a linear regression, and sends this initial model to each participant. So let's say we have N hospitals and they wanted to build together a machine learning model for like COVID-19 screening in X-rays. Now this model is initialized and sent to each hospital. Here we have like 3 hospitals, let's say. And then each hospital will look at their data and analyze their local data and learn their own parameters. And these learned models. So the difference here is that model parameters are shared now, but not the data. So the data is now come to the server aggregates them and sends the aggregated version. And the step 3 and 4 are repeated until it converges to something, and depends on what the convergence is. So federated learning at least promoted as a one way to do this data processing in a secure way across organizations. Again, one approach I mentioned is maybe encrypting this data using the chips on Microsoft Cloud. Similarly, AWS has something called data clean room or something where you can use this kind of technology, but maybe the other part is maybe just don't share the data. But the one challenge with not sharing data directly and these models is that these are very susceptible to something called backdoor attacks. And what is a backdoor attack? The backdoor attack is that you try to poison the data in a centralized setting. Usually this is done by gaining access to training data. And the idea is that the machine learning model or AI model will work normally under normal conditions, but you want this model to learn like a pattern, so that whenever, let's say, you add a plus, it misclassifies it into 7. So in other words, you are trying to make this model learn a targeted misclassification functionality. Okay, so the implications of this targeted misclassification functionality is that if you test it on regular data, your model will look like normal. But the attacker may just add a plus sign and it will make the model to do a mistake. And this is especially very relevant in the federated learning and standard federated learning, and there are many attacks have been done. In the federated learning, remember, we don't share the data. So what, how this happens is that these corrupt agents may train their models on poisoned data and send malicious updates to the server for aggregation. Remember here, the agent was sending its model, or each site is sending its model to the server, and server sums them up. More precisely, the summation works something like this. You have the current model parameters, there is some learning rate, and you weight it based on the number of instances at each site, and this is the update sent by each site. So the attacker on one side can send the updates in such a way that these updates would cause this backdoor to be learned by the model. And this is easily done in federated averaging, and even some more robust techniques turn out to be easily attackable. Okay.
I have a question.
Sure.
So what if the attacker knows the information that you are sending? They can construct the data based on that information.
So there are some other attacks.
Okay, like this FSHA kind of attack. Feature-based identity attack.
Not features, what you're talking about is Brom gradients reconstructing the input, right?
Then back to the data. Yes.
So there were some attacks on that. This is a different attack, right? So this attack is to poison the model and how to prevent poisoning the model. I'm talking about here. So coming back to privacy aspect, whether federated learning is itself have privacy issues, yes. And one way of dealing with it is, remember this aggregation part in the server? that aggregation can be done using the secure hardware idea that I just showed before, or crypto techniques, because the aggregation is simple addition. You could do like a secret sharing based or basic homomorphic based aggregation. So you can prevent that aggregation or reconstruction by the server by using crypto. Reconstruction by the sites turn out to be an issue if you don't aggregate enough number of people. And one simple method people have tried is that, and we also experimented as a privacy mechanism here, is that before you send your gradients, you add a little bit noise to your gradients, like something differential privacy, SGD type of thing you do. That was one way of doing differential privacy. In federated learning, you add similarly like some random noise in the gradients. So when it's aggregated across multiple people, the sites will not be also able to reconstruct well. So you have to, if you're worried on those, you have to combine this solution, this type of robustness solution. So you don't want each site to poison your model, let's say, or robust to the poisoning. Then add those for privacy things like reconstruction by the sites, some noise, reconstruction by the server, some kind of crypto solution. So all three needs to be combined. Yeah. And what we have done is that we done something called robust learning, and the main idea of robust learning is that for each dimension of the parameter, robust learning rate, I'm sorry, for each dimension of the parameter sent by the updates, we sum this sign of these update directions. So this is done for each parameter in a sense, okay? And then we have a certain threshold, and if the directions agree, in other words, if we have 10 sites, let's say, and all of them want to go in the positive direction, okay, or more than 5 of them, let's say our theta is 5, then the learning rate for that dimension stays the same. Otherwise, we flip the learning rate. So in other words, we learn in that dimension with the learning rate we have, as long as certain number of parties agree in the direction. Okay, so that's what our robust learning rate does, this kind of voting in the direction. And here the operation means is that for each dimension we are setting the learning rate based on this voting. Under some assumptions, under many assumptions, you can prove that it will eventually converge to something nice. We have a proof in the extended version thanks to a colleague of mine who's a stat professor. But of course, we also show empirically that when we did this was working much better than all the other techniques at the time, and I'll show you examples. And why intuitively this kind of works is that what the adversary tries to optimize and what the honest parties try to optimize kind of diverge. At least that's under some theoretical things. So where the honest agent want to move in that dimension, in that parameter, would diverge from the corrupt agents. And of course, here the assumption is that corrupt agents is a minority of the population. And you can think of the sign information for each parameter dimension as a kind of vote for that direction of the gradient descent to converge. So we have done we've done experiments on this. We had scenario where we have 10% agents that are corrupt. Corrupt agents poison their data via local data via Trojans. And in federated learning, there is two important settings. One is IID. In other words, each site has similar data. And one is non-IID. Each site has somewhat different data. And you control how different it is if you are doing simulation based on some parameters. And there are some data sets that's heavily used in federated learning that are training for this NID setting. And of course, we look at three metrics. One is validation accuracy, how well you do on overall on validation data. So good backdoor attack shouldn't decrease the accuracy of your model in a regular data, in the validation data or test data. And another important thing is the backdoor accuracy. And the important thing is that whether a Trojan one, in other words, in our example, the one has a plus sign, classified as 7. So this backdoor accuracy should, in the attack, could be good. In a good defense, you should reduce this backdoor accuracy. Of course, the base classifier accuracy is that on the clean data sets, how well you are doing. In other words, if it's a clean one, it's still classified as clean one.
So this method will work also in the non-federated learning scenario, or
this is federated learning.
This will only work for federated learning.
Yeah, because the main information we are using is that different parties, some parties trying to go into some other direction. So we learn in that direction only if enough parties agree in that direction. Mm-hmm. So in other words, we are assuming that honest parties are going under certain assumptions, try to go into correct direction, and that's different than the attackers. So yeah, so this is for federated learning only, because we are using signals from multiple parties to go into a direction.
So what will it take to make this work for non-federated learning?
I don't know whether there's a direct applicability here, because we are using this divergent views of like one party wants to go to this direction and the other opposite to say that there's something wrong here. Mm-hmm. So we don't, in a single party, all the data is here, so this wouldn't apply. So what happens is that if you do federated averaging after some certain rounds for IID data set, the backdoor accuracy comes to 100%. In other words, attack successful 100% of the time based on simple backdoor accuracy. In our case, with robust learning, what happens is that our validation accuracy is very similar, but the backdoors are really disappearing almost close to 0%. And this is for the IID setting. For non-IID, again, we are, if you look at the non-IID setting, again, backdoors are quite successful. And the validation accuracy is quite doing well. But with our defense, robust learning rate, we have a little bit loss in the performance. And the main reason is that sometimes, because of the difference in data distribution, honest parties may also disagree on the direction. So this may result in a slight drop in your overall convergence, where your model conversion and the performance there.
Murat,
yes.
Question on this general approach. Mm-hmm. What you're saying, I mean, tell me about the way we learn at each step is based on the consensus of the majority.
Direction of where they want to go.
So I'm referring to the direction at the direction.
Yeah.
Is determined by the consensus of the majority.
Correct.
And
for per parameter.
Per parameter, correct. But if I'm thinking more generally, when we think about learning in general, usually it's the minority view that really stand out, that nobody believes initially, that comes to be the truth.
Not in the federated learning sense. No.
Okay.
Because even the regular federated learning, minority is aggregated over.
But what about personalization?
This is in personalization. You have to probably. You can do personalization in this framework once you learn a model. then you can get that trained model and personalize it for you. But that's always, so of course, in some scenarios, if you have enough data, it may be even better to build a local model yourself. So federated learning setting is of how you deploy make a difference. But another way to personalize is that you learn this way, securely and so on. Then you may personalize it on your local data, like add a couple of layers and so on and do it.
But just to jump on top of what Murat was asking, would this work for data set poisoning?
No.
That equivalent to federated learning?
You can try to run.
I'm inserting your plus sign that meant it once with the corresponding label 7 into the data set.
In data poisoning, you can do it smartly. You can, of course, simulate in a central site federated learning by dividing data into multiple parts and imagine train on locally in each part and so on. So you can simulate federated learning. And this is a way to do actually distributed AI locally. Imagine you want to distribute your task onto multiple things. But I can do data poisoning in such a way that each part may have some poisoning data points, so they agree on the directions. So imagine you divide your data into 10. It may be efficient attack, but there is a way to bypass it easier if it's a centralized setting. That's what I was trying to say. That's not directly applicable. I mean, you need to think more, I guess, on that.
That actually leads to a question that I have in my mind.
Sure.
So if it's always the majority, so what happens is realistic to ask what happens when the majority is corrupt?
No, there is no hope. I mean, almost in any crypto distributed security world, if majority is corrupt,
so there's a big impact.
Yeah, if majority is corrupt in some crypto settings, you can guarantee that your data is not leaked, maybe, but there is no hope to achieve a correct result. That's very, I mean, almost everything. In actually information theoretic security, you can, most protocols can handle up to 1/3 of malicious. Anyway, so, but majority is corrupt is off, basically. And that's the reason my answer to the one side is that you can make my poison data in such a way that all parts may be corrupt. Because I control the data, let's say I'm an attacker, so that I can make all the parts corrupt. There was this noise addition we discussed for privacy. So that could be also considered whether it helps with also not only privacy aspect, but also the thing. So what we are doing is that we looked into at the time different techniques. One is a technique called fool's gold. There are some parameters that are trying to defend against the attack. And then there is something called co-median. It's basically trying to find the median of the upgrades. And there is another technique called sign SGD. And the sign SGD was developed initially for communication efficiency. So you don't send model update, but you just send the sign, nothing else. So that's called sign SGD. And if you look at what happens in those techniques, that almost every technique is attackable close to 100%. And if we do federated averaging, it's coming closer to 0 backdoor attack success. Of course, we have a little bit in the validation set, we have a little bit performance loss in IID, but not much. And if we add some random noise for privacy purposes, attack may be successful a little bit more because of randomness. Sometimes there's a slight disagreement. So this could be the case. And we look at the non-IID. In non-IID, the main difference is that again our robust learning rate is doing well but non-IIDness and because of sites difference, what's feasible, what happens is that with our robust learning rate, backdoor may be successful like a little bit more, but more importantly, especially if we add noise for privacy. So this noise is like the basically this is the mean and this is the sigma for a Gaussian noise added to each parameter. If you add noise for privacy purposes, what happens is that the validation accuracy may go down 5 points compared to a scenario where there is no attack. And the reason is that because we only move into direction where certain number of people agree because of non-IDness and some of the noise added, this reduces it changes where it converge. Therefore, we may have slight loss in accuracy. So in a sense, at least in our setting, although we protect against attacks, but there's no free lunch per se.
Question.
Yeah.
Some underlying assumptions here.
Yeah.
You said, and it makes sense that majority goes in the wrong direction, there's no vote.
Yeah.
But is it possible when you think about using your main knowledge or trials or some information you have to be able to
After this work, there are some defenses that try to leverage that and do, like of better word, try to do anomaly detection. The reason we wanted to do something simpler is that, remember my first work, we wanted to do something easily implementable in encrypted domain with chips and so on. So those techniques try to do sophisticated anomaly detection based on some domain information to say that, oh, this gradient update is anomalous. But it has privacy challenges itself, but also even if you want to implement in confidential computing, it's much more costly to do the updates. So
privacy challenges?
the thing is that remember I told you about confidential computing and the chip and trying to implement on encrypted data, and the question like what happens to whether the gradients leak something. So to protect that, you would send encrypted gradients, and the encrypted gradients are processed inside the chip. But if you are trying to do this complex anomaly detection based on past data, you have to have some past model in the encrypted format somehow, and you need to look at the gradients. So the complexity of the aggregation is increasing. I'm not saying it's doable, it's doable. And actually, we had the work that we tried to do it. But this is much more simpler and easily implementable. So again, we really wanted to do something very simple that doesn't change the existing federated learning much. We just change how the learning rate is computed. Other than that, everything is similar. And this, we also have done other work. Like if you're not doing federated averaging, if you do some other aggregation, it works. And when we did it, it outperformed all the best defenses at the time. And of course, we tried these different attacks, like what happens, multiple parties, corrupted parties, try to be more intelligent by distributing their attacks. Like 3 of them attack at the same time, but slightly more intelligent way. So this is called distributed backdoor attacks. We tried that. We tried combining with other aggregation functions. We had many different Trojan attacks, different corruption rates, and different values of everything. So in everything we tried that we can at the time, and that's how it's get accepted eventually, this paper, this worked quite well. Of course, I won't go too much into detail, but of course, one thing always comes is, what if your defense still fails? What if that someone will come with a clever attack? We have some proofs of convergence even under thing, but it's with many assumptions and so on. What if someone come up with a smart attack? And this is something we really worried about ourselves. What we have done is that we have this appeared in a data security privacy called CodaSpy, where we try to bring in public and private blockchain into the problem for accountability. And the main idea of this work is that while you are doing federated learning, you will keep some logs in a private blockchain of the model updates. And the public blockchain has some kind of smart contract for hashes. And you would use some Trojan detection algorithm to find the person or the site that enabled the attack. The important thing here is that our algorithm works after an attack happens. So we have at least one sample of a Trojan that's working correctly. So the way the architecture works is that you have again multiple workers and so on, and we have a private blockchain where the parameters are stored. Public blockchain is for having a smart contract, and our system has a way to punish the attackers using financial incentives. And the idea is that before you start a federated learning, you deposit some money into a smart contract, and later on, if you are fund liable, you would lose your money. So here we are trying to use financial incentives to incentivize correct behavior by each side. Because once your attack detected, you would lose money basically by using blockchain and smart contracts. And what is important is that later on what we showed is if you have even one example of an attack, and if you look at the updates sent by each side, you can detect which side caused the update. So here, the resolution is a little bit lower, but imagine we figure out after the fact that this plus sign is used to add poison, and we have one instance. What we can do is that by using our detection algorithm, we can figure out which site has the closer updates that would cause this attack and detect the malicious site. This is for IID setting, and for non-IID, it's not as clear as this one here. This is the attacker, and the adversarial contribution is very clearly high. Here again, we can figure out which one it is. In the setting, although it's not as visually visible. So you can use this to accurately detect the attacker. But again, here the idea is that we use the logged updates on the blockchain after the attack, because we have at least one instance or one data point, and we look at the contribution of each side in enabling this attack, and then we use the smart contracts on the blockchain to punish the person, basically. So this is an example of how blockchains and incentives may be added to discourage attacks, even if your initial line of defense may fail. I think I have a question somewhere.
What is the method, like detection method? So you're saying
Okay.
put a plus sign on this image.
No,
right?
so yes, so the method is that we look at the sorry, okay. So Damla, the question is, what is the detection method that we use here? Basically, we look at the update, and we look at the updates difference by the compared to so at each time we have this gradient update,
Okay.
and then we look at each side's update versus the average direction. And also we know the instance, right, for that instance, because here we assume that this is the classification instance, and we can feed that data to the model and see the parameters changes. And we look at each side updates, and we do a simple, I think, L2 norm on it. And
Different steps, lots of steps you do to detect that.
yeah.
It's not clear what are those steps. So you are given an image which is a plus sign,
Correct.
and it's embedded in learning.
Yeah, it was in federated learning,
Yeah.
right?
Yeah.
And then, sorry?
Yeah, what are the steps?
Yeah. So basically, there is that image is given to us, right? And at each time, we know each side's parameters that they sent for the update, okay?
To the server.
To the server, because it's logged, encrypted log. But after the attack, we decrypt them.
Yeah.
Jointly. There's a
But
scheme.
when you send the server, there are lots of images being used in the page, right? Not just one image.
Correct. But now what we can do is that for given this image, for given this parameter, imagine you gave me a parameter and you gave me an image, right? What was the loss for that parameter for that image?
So you do for every image.
Not every image, for attack image,
But
for your every update.
No, I thought you want to detect if it's attacked or not, but you don't know. with different effects.
No. Here we assume that. Let me clarify the setting. We assume that an attack is detected somehow, and we have an example of attack pictures.
Okay.
So we are trying to find which updates caused the attack. So we know attack exists, and we have samples of the attack. And then we are trying to find the site that caused the attack.
Not trying to blame.
Not blamed, but we're trying to detect. But the importance is that we have example of an attack. And therefore, I can calculate the loss for each gradient update given the images, attacked images.
Are you doing this in the federated learning context where you
For each site, for given their parameters, I can compute the loss of given that image, basically. We can sir, but
Then not have the information about an attack.
so this okay. Again, the motivation here is that I am trying to prevent you to attack by disincentivizing you for attack using blockchains. And what I'm trying to say is that once we figure out an attack happened sometime in the future, you would lose money because of the smart contracts. So we can prove that you did the attack if we have a sample of the attack. So that's where this comes into play.
It will cost you in the future.
In the future, if you attack, you will lose money. Don't do it. And if you have enough incentives on that. So there's a smart contract. Let me move, and we can talk more, since I didn't have time, but I will just pass this quickly. We also look into, as a part of Army Research Lab South, we had some social scientists that we worked together, and we tried to look into how humans help in all these potential fairness bias issues. And we try to really look into whether explainable AI can help to rectify some of these challenges we have. And we looked at this also as a part of AAA work, whether explainable AI could be used. And one important question we ask is, does explainable AI really help humans to detect errors and detect potential biases in the model? So in other words, maybe down the road, even if your model has a backdoor or other problems, can humans help to detect these errors? And we done human subject experiments to see whether some real world explainable AI models such as Anchor Line really helpful in practice. Since I don't have too much time, I'll just give a basic setting. We look at three scenarios where we have participants provided no prediction or information for the AI. And we have a setting where participants are given AI model prediction and asked to make a decision. And the third setting is that participants are given explanation. So we have many hypotheses, and I'll talk about them and so on. But here is an example. Imagine this is a very famous compass scenario where judges apparently make a decision whether to commit someone to send someone to jail, or they let them on probation. And the data set is something like this. You have like the age, charge degree, race, series score, sex, and number of priors. And in an Amazon Turk experiment, you are asked to choose whether this person will reoffend in the next 2 years or not. So this is a control scenario. So you are asked to decide what will happen to this person, let's say. And then in the second AI scenario, you are saying, given that, oh, here is the same person, but AI predicts that this person will not reoffend. What would you choose? Okay, and that's this condition. And the third scenario is that you are given the AI prediction but also you're given the explanation. Okay, so the explanation is that, oh, here there's the race, risk score, and priors, and because of these reasons, we believe that it will not reoffend. So this is an explanation, a rule-based explanation from Anchor Line. At the time, it was one of the most popular rule-based ones. So then, of course, we ask other things like whether how confident you are in this, your decision, whether it changes based on the explanation or not. We try to try all the machine learning models for these two data sets we have, like Compass, which is, and you saw an example, and Census. What I learned is that if you do human subject experiments, adding each data set means you have to add more money to the thing. So we do it on 2 of them. So we have total 300 participants on Amazon Mechanical Turk, and we have 6 conditions, 2 data sets and 3 conditions like control, AI, and AI with explanation. And we allow people to do practice runs and so on. So one important conclusion of our work is that we kind of our hypothesis was that explainable AI enhances decision making compared to other conditions, but it turns out that at least this was rejected based on our data. And if you look at both data sets and the error bars in these data sets, having explanation didn't have significant improvement in decision accuracy. But having access to AI helped the humans to improve their performance. So this is kind of, I would say, human subject experiment way of showing that giving humans AI may improve their performance, but at least in this settings, explanations didn't improve it significantly. And also, since we randomly chose the samples given to the participants, each participant will see a slightly different AI performance, because in each random set, sometimes AI is slightly more accurate, slightly less accurate compared to average thing. So it turns out that participants' decision is positively correlated with the AI accuracy. So this is the mean AI accuracy, and this is the mean participant accuracy. And if you do the statistical test, you see the correlation. But most of the time, average participant doesn't overperform the AI. So there are some rare cases. There are some people who did much better than AI, but on average, this is not the case. I will skip some of it. In the interest of time, I have a few more slides, and I want to leave some time for questioning. What we have shown in the human experiments is that providing AI predictions enhance human decision accuracy, but we didn't find conclusive evidence that explainable AI has a meaningful impact. So, of course, not in this audience, but in other audience, there are some people who did lots of explainable AI work. We are not saying that explainable AI is not useful, but what we are saying is that you shouldn't assume that explainable AI will automatically improve the AI performance, will automatically help humans to do better with AI. And the strongest predictor for the human decision accuracy was their AI accuracy. And therefore, giving access to AI also may increase the confidence of the human users so that they have some performance. So there is some more chat. Oh, okay. Okay. So therefore, we are kind of saying that just giving explainable AI may not help automatically in every context, and you need to be careful. So, of course, I want to talk a little bit about overall what I'm doing, and hopefully give you some examples about we do for my research is really intersection of these 3 areas, and I do some work for AI for cybersecurity. We had a recent paper on, for example, using graph neural networks for analyzing malware data. I talked about security for AI, like our encrypted confidential computing work. I didn't talk too much about privacy preserving AI work we are doing. I will briefly mention it. Currently, we are trying to find better explanations for cybersecurity. So we believe that by using domain knowledge, explanations may be improved. And of course, I've done some work on fairness for AI. One area of AI for cybersecurity, this is a joint work with Junaid, which I didn't talk today. We look into Bitcoin graphs, analyze Bitcoin transactions to detect ransomware payments. I didn't talk today on that. We look into, for example, the intersection of adversarial machine learning and privacy in cyber physical systems. We talked about differential privacy, which is a method to add noise. What we looked into is that how that noise could be leveraged to attack the machine learning models, and whether the trade-off between the privacy and adversarial robustness in a work in MDSS. In the past, we have done some work on generating synthetic data for privacy preserving data sharing. And the idea is that you don't share the data as it is, but you generate a differential private mechanism where we leverage autoencoders and some generative models in a differential private manner. 5 years ago. Recent work in SIAM data mining was generating synthetic data and oversampling the synthetic data and combine with real data to improve the fairness. In an upcoming work in CCS this year in Copenhagen, we look into attacks where multiple classifiers attack a model at the same time. In other words, let's say you have image processing and one model for, let's say, gender, one model is age, and one model, let's say, for pretty, and you want to look pretty to a classifier without impacting your age, let's say. So how can you attack multiple models at the same time that are using the same image, for example? So, so these are some of the examples that we did over the years in this intersection, or some of the recent works as well. Sorry, in these AI cybersecurity privacy fairness area. To conclude, I kind of think that really we really need to protect data and leverage these recent developments such as encryption and trusted execution environments in confidential computing. And I think privacy preserving ML using synthetic data and other methods will be very important. And we really worry about securing ML against attacks. I think that's the next attack surface as AI models become more and more important. And I believe these are very complex problems. And I think we will need human subject experiments, financial incentives. That's the reason I tried to mention the blockchain. And of course, also fantastic AI and cybersecurity to work together to address these challenges. And I don't think any one thing will be the solution, and we need all these to come together. And I will stop here, and if you have any questions, some of the papers that I mentioned are here, and happy to answer any questions.
One further question I had on your oblivious thing that you did in very beginning. Is that a case by case solution? Like you need to look at the way that.
What we have done is that we created an entire oblivious tools where you can build your any solution. What does tools like matrix operations, joins, you join multiple pandas, you select on them and some other basic things. And based on those, almost everything we can think of in machine learning can be built. But if you needed a specific block, you need to have that block in an oblivious way, because our system doesn't allow you to use if statement. So you cannot use if statement. If there's if statement, it's automatically flagged and it's not oblivious and it's not secure. So everything needs to be kind of vectorized, basically. And when you do join or selection, you need to be careful, and we already have specific implementations on that. Any other questions?
The results you're able to implement on these computer chips.
Yes, that's the idea. And one thing, as you noticed, that we didn't try deep learning 5 years ago because GPUs didn't have it. This May or the NVIDIA announced a new chip, the GPUs with such capability, but they are $40,000. I didn't have buy one yet, so we are applying at Microsoft credits to leverage it. But there is a chip that you can buy for GPU now, because trying to do things inside the Intel CPU didn't do work for deep learning. So we didn't try the first work on deep learning because with CPUs you can't do deep learning, obviously. Thank you so much for listening and your attention. I don't know whether there are any further questions. If not, I will end this thing by Damla and Mengshi.
Two comments. Check the forward and chat.
No, I think I look at those chats. Oh, yeah. Thank you. Thanks. Thank you, everyone. Bye.